We're going to do some Friedel-Crafts alkylation. We're going to go over several reactions and we're just going to predict the products, okay? So what if I take benzene, okay? What if I take benzene and add chlorine and aluminum trichloride? What would be my product? Well, I'm going to generate chlorobenzene. Okay, all I'm doing is adding chlorine to my aromatic ring. Okay, if I take benzene and I add Br2, and let's use aluminum tribromide, still a lowest acid, I will generate bromobenzene. Okay. And what's interesting is that if I take nitric acid and sulfuric acid, I will get this nitric group here. Okay, so this is actually a very important molecule because we're going to do a lot of chemistry with this molecule. But just remember, when I take so this video is Friedel-Crafts Alkylation along with Electrophilic Aromatic Substitution. So we're just substituting things on the benzene ring. Okay, when I take nitric acid and mix with sulfuric acid, I generate some sort of NO2 NO2 plus. Okay, and then my benzene attacks. Okay, so just remember that whenever I take sulfuric acid and nitric acid, I'm gonna get on my nitric group. So what if I take benzene, okay, and then react it with sulfuric acid, which is fuming, okay, it's very hot. I will get this product. Okay, this is called benzene sulfonic acid. So benzene sulfonic acid, BSA. Okay, so when I take sulfuric acid, fuming sulfuric acid, I will generate SO3H. Okay, now some books also describe this as just SO3. So if you take SO3 and some sort of lowest acid, you will get the product. Okay. So if I take SO3 and aluminum trichloride, then I'll just add SO3 to the ring. Okay, but either or is fine. Okay, so what if I take benzene and I use methyl chloride and aluminum trichloride? What will be my product? Well, I'm going to generate toluene. Okay, my chlorine leaves, and I'm going to generate toluene in my R group. Okay, now what if I take benzene and add methanol, okay, and aluminum trichloride? Here's what I get. You get toluene, okay? So just remember we said that Friedel-Crafts alkylation, or for the electrophilic aromatic substitution, I could do these with any. It could be chlorine. I could do this with an alcohol, and we could also do it with alkenes. Okay, so just remember that. So what if I take benzene and I add FeCl3, still a lowest acid, and in the first step. Okay, so what if I react these in the first step and benzene in the second step? What do I get? This is the product I would get. Okay, I'll be bonded to the plus charge that will be created. All right, so I'm bonded right in between the metal. Okay, so what if I take benzene plus this molecule here in aluminum trichloride? What will happen? Well, this is a product you would create. These are called mezetylene. Hope I'm spelling this right. But mezetylene, okay? Wow. So look at the difference between this and this. How in the hell did I get this product? Right? Some people might say, oh no, I would actually get this. Okay, so I'm just gonna draw my pH, which represents my benzene. And I would get my pH that would be bonded to this. Okay, some people get this, and this is wrong, incorrect. Okay. Because we get carbocation rearrangement with Friedel-Crafts alkylation, I'm gonna always create my product on the more stable carbon. Now, one might say, okay, well, this carbon is primary, and this carbon is primary. So, what's the difference? Why did it move from here to here? It so happens that because we're dealing with benzene, the carbon that's usually in the middle, that's sandwiched in between the middle, even though they're both primary, it's still more substituted because it's bonded to two carbons. Okay, versus this one that will just be bonded to one carbon. Okay, so if I'm looking at this carbon will be bonded to one carbon, which would be less substituted. Okay, so that's the difference. So again, be careful. We get carbocation rearrangement, and the middle carbon is usually the one that my electron will be bonded to. And simply, if we want to draw this out in solution, we created a plus charge here. Okay, we created a plus charge here, and then we sacrifice one of those hydrogens and move our plus charge to the middle. Okay, so notice the difference. I have carbocation rearrangement. Okay, notice the difference. This is more substituted than this here. Okay, so let's look at another example. So what if I take this molecule here and I react it with benzene and some sort of aluminum trichloride and Lewis acid, some sort of Lewis acid. What will be my product? Well, again, carbocation rearrangement. So I'm going to generate my plus charge on this carbon, but it's actually going to move. Okay, I'm gonna move the plus charge to the benzylic carbocation, and so therefore, that being said, I'm going to create my benzene. That will be, well, my alcohol will leave, so my benzene will be bonded to this middle carbon here. My benzene will be bonded to this middle carbon here. Okay, we bonded to this middle carbon here. Now look what I have on the middle carbon that's branching off. I have a methyl group, so let's put this up. So if I have a methyl group that's bonded, well, the next thing adjacent to it is the whole pH group. Okay, so I'll get this product. Okay, so look very carefully. I should generate a plus charge on this carbon, but because of carbocation rearrangement, I'm gonna get it on the middle carbon or the benzylic carbon. Okay, and so this is why we form this product. Okay, so very important. So now what if I take hopefully you can see this. What if I take benzene and I react it with propylene? Okay, and some sort of Lewis acid, I will get mezzanine again. Okay, I'll get mezzanine. Okay, now with alkenes, again, with alkenes, I'm going to generate my carbocation on the more substituted carbon. So, so what does that mean? Okay, so for alkenes, just remember that I will generate my carbocation on more substituted carbon. Now, if I look at this is a CH2 here at the end, so it has two carbons, but this only has not two carbons, two hydrogens, and this only has one. Okay, so this is way more substituted than this. Okay, so that's why I will get my bond. The pi electrons will attack I'll get carbocation rearrangement, and then we'll attack the carbon that's more substituted. Okay. Now, what if I take this molecule here and I react it with let's see if I react it with benzene. Okay, I react this with benzene and aluminum trichloride. What would I get? Well, look at my carbon-carbon double bond. It's symmetric, okay? It's symmetric. So in this case, it doesn't even matter where my benzene will go, okay? Okay, so it doesn't matter in this sense, okay? So if you want to draw the product of this, I could say, okay, well, I'm going to have my benzene. That's going to be bonded to one of my carbons that I'm going to lose my double bond. So let's put another phenyl group here, okay? Let's try. This is not an alkene, it's a phenyl group. Yeah, so I'll get that. I'm gonna lose my double bond. Okay, I'm gonna get this product. This is a phenyl group. Okay, so that's the product that I will get with two hydrogens here. Okay, now what's interesting also is that if I take benzene and I take propylene, well, not propylene, I'm sorry, but ethylene oxide, okay? If I take ethylene oxide and some sort of Lewis acid, okay, so let's use FeCl3, I would get attack on the more substituted carbon, but look at this. My carbons are symmetric, okay? They're equal, they're both primary, and so it doesn't matter which carbon I attack, okay? So when I generate, okay, in the Lewis acid, when I generate my positive charge, my benzene, one of the pi electrons from the benzene, I'm just going to draw in some pi electrons here. It's going to attack, okay? When that attacks, I got to break a bond, okay? I got to break a bond. Now this gains protonation. This will gain protonation in the solution, okay? And we're not going to go through the mechanism here. What I'm just going to show you is how the bond is made, okay? So one of the pi electrons use it as a bond. So we get bonded to one of these carbons, okay? So we get bonded to one of these carbons that has this carbon floating along and our OH on the end, okay? So we get alcohols. So that's the idea that I want you to get. With benzene rings and epoxides and Lewis acids, we create alcohols. Okay, let's do another one. What if we take benzene and add this reagent here and some sort of Lewis acid? What will be my product? Remember we said that with Friedel-Crafts alkylation, we're always looking for the more substituted carbon, same thing, EAS reactions, we're looking for the attack on the more substituted carbon. Okay, so if I'm looking at this, this is my more substituted carbon versus this, okay, this is primary. This is secondary, I have one hydrogen here. So look, I'm gonna get attack. I'm going to be bonded to this carbon, okay, that has a methyl group, which is this group here, as a methyl group, and then one carbon away, I have my alcohol, okay, because once I get attack on this carbon, I got to break this bond, which the oxygen will actually gain protonation in the solution before. Okay, and so this is the product that I get. So that's all I have for the general reaction scheme and in general. I just wanted to show you that be careful with Friedel-Crafts alkylation. There's always room for carbon cation, and we're going to get attack on the more substituted carbon.